You can factor any polynomial of degree n into n linear factors, but sometimes the factors will involve imaginary numbers. It is easy to see graphically that every polynomial function of degree 1 has a single zero, the x-intercept. However, there appear to be three possibilities for polynomials of degree 2. Consider the following three graphs. First on the left, y equals x to the fourth power minus 4. It has two real zeros. Note that x squared minus 4 can be rewritten as x minus 2 times x plus 2. Setting that equal to 0 reveals the two real roots, 2 and negative 2. Next, the graph of the equation y equals x squared minus 2x plus 1. It has one real zero. Factoring the quadratic expression x squared minus 2x plus 1 to be the product of the binomial x minus 1 and itself reveals a root of multiplicity 2 at 1. And our third graph, a parabola that doesn't intersect the x-axis at all. This equation, y equals x squared plus 2x plus 2, has no real zeros. Note we can rewrite x squared plus 2x plus 2 as x minus negative 1 plus I times x minus negative 1 minus I equals 0. That reveals two complex roots, negative 1 plus I and negative 1 minus I, but no real zeros. By factoring, however, you can see that each related equation has two roots, regardless of the number of real zeros. Every quadratic polynomial equation has two roots. Every cubic polynomial equation has three roots, and so on. This result is related to the fundamental theorem of algebra. The German mathematician Carl Friedrich Gauss, who lived from 1777 until 1855, is credited with proving this theorem. Take note, theorem, the fundamental theorem of algebra. If p of x is a polynomial of degree n, and n is greater than or equal to 1, then p of x equals 0 has exactly n roots, including multiple and complex roots. Problem 1. Using the fundamental theorem of algebra. What are all the roots of x to the fifth minus x to the fourth minus 3x cubed plus 3x squared minus 4x plus 4 equals 0? First, consider what you know. You know the polynomial equation has degree 5. There are 5 roots. Then consider what you need. You need the zeros of the function. So your plan? Use the rational root and factor theorems, synthetic division, and factoring. Step 1. The polynomial is in standard form. The possible rational roots are plus or minus 1, plus or minus 2, and plus or minus 4. Step 2. Evaluate the related polynomial function for x equals 1. Since p of 1 equals 0, 1 is a root, and x minus 1 is a factor. Then use synthetic division to factor out x minus 1. Reversing the sign from negative 1 or minus 1 to positive 1 in our half rectangle. Extracting coefficients from our expression, 1, negative 3, 3, negative 4, and 4. Dropping the 1 and performing synthetic division. We find 1, 0, negative 3, 0, negative 4, and a remainder of 0. Step 3. We'll continue factoring until you have 5 linear factors. Note x to the fifth minus x to the fourth minus 3x cubed plus 3x squared minus 4x plus 4 can be written as the product of the binomial x minus 1, as established in step 2, times the trinomial x to the fourth minus 3x squared minus 4. The result from our synthetic division. Now x to the fourth minus 3x squared minus 4 can be rewritten as x squared minus 4 times x squared plus 1. And these binomials can be further factored, x squared minus 4 being a difference of squares, and x squared plus 1 being factorable as x minus I times x plus I. Our completely factored form, x minus 1 times x minus 2 times x plus 2 times x minus I times x plus I, reveals 5 roots. Step 4. The roots are 1, 2, negative 2, I, and negative I. By the fundamental theorem of algebra, these are the only roots. Your turn. What are all the roots of the equation x to the fourth plus 2x cubed equals 13x squared minus 10x?